Hello, good morning. My name is Suryasit Yangsao. I was an instructor of technology 40 years ago at a trade school called École Enseignement Général et Professionnel dans la province de Québec, in the province of Quebec. At the time, I taught electrical circuits and electrical machine. Since I am a retired man, I want to refresh my memory of the knowledge I have acquired in the field of electrical circuits. Today, I am interested in dealing with a balanced load of delta connections. I want to prove again that the line current of a balanced load connected is equal to root 3 multiplied by the phase current with a phase of 30 degrees. To prove this, I will use relations between a current and a voltage using also an impedance of the same value in a delta connect balanced load. As source, we consider a three-phase delta connected with the voltage VAB, VBC, and VCA, and the current from the source will be IA, IB, and IC. As for the load, we consider a balanced delta connected with the impedance Z delta in the load circuit. And we should know that every phase current is equal to the voltage applied to the phase divided by its impedance. We want to demonstrate that the line current is equal to the square root 3 of the phase current. It is well known that the angle between the line current and the phase current is always 30 degrees in a balanced delta connection. On this diagram, the three voltages are of equal value and are separated by an angle of 120 degrees. Usually, a current can either lead or follow the voltage applied on the impedance. Here I consider a phase angle phi between the current and the voltage. because the voltage are of equal value and follow one another by 120 degrees, the current will also be separated by 120 degrees. Please watch carefully the diagram below. The three currents in the three phases are represented here by IAB, IBC, and ICA. They are separated by 100 degrees from each another and from the source, and is equal to the difference of two phases of the delta connections. The line current from the source IC is equal to the phase current ICA minus the phase current IBC. So I can say that minus IC is equal to IBC minus ICA. Now, if you draw the vectors that is opposite of the current ICA on the first quadrant, you will see that vector minus ICA that form with the current IBC an equilateral triangle, because at the summit O you have a 60 degree. So divide by 2, you got 30 degree each. If you draw the vector representing IBC minus ICA, you will get the vector minus IC, which is a line current. In the triangle of the left, you can see that half of the current IC is equal to the phase current ICA by a cosinus of 30 degree. The cosine of 30 degree is equal to the square root 3 divided by 2. This means that half of the line current is equal to the phase current multiplied by the square root 3 divided by 2. That means that the current itself is now equal to the square root 3 of the phase current. And you can see that there is also 30 degrees between the two currents. Now let's remember that the line current in a delta balanced load, you have the relationship which is the current of the phase equal to the line current divided by square root 3, or the line current is equal to the phase current multiplied by the square root 3. Next step, I will give you an example of a balanced load delta. As exercise, I will give you the impedance of the phase, and we will calculate the current of the phase and the line current.